Oh, perfect. Okay. Thanks, Anthony. Thanks so much for coming. We're really excited to get started for this month's GeoDAWG seminar series. For those that are new, please sign up for our mailing list. We send out a lot of information about upcoming workshops and anything related to data assimilation. So please, if you haven't signed up, please do so. We'll send those out periodically. Also, our seminar list will be updated on our website, which you found because you've seen the Zoom link. But our next seminar will be given on November 1st by Humberto Gutierrez. So please come back in about a month time for Humberto's talk. As with all our talks, we will record them and then upload them to our YouTube channel so that you can come back and view them in the future at your own time. So if you haven't subscribed to that, we have over 40 subscribers now, which is exciting. And then we're also taking recommendations for speaker suggestions, which you can input those on our website as well from the link here or just going through our website. So if you know of someone that is really interested in this type of work or would give a really good talk for generating discussion, please feel free to input their name and then we'll reach out to them and schedule them for a future time. All right, so without further ado, I'll pass it off to Anthony, who will introduce our speaker for today.
All right, hello, welcome back, everyone. Just again, everyone's pretty used to Zoom by now, but please keep yourself muted. And Clayton is happy to answer questions during his talk, so feel free to jump in if you see a good time. Otherwise, you can raise your hand or put the question in the chat, and then Adam or I can jump in for you. And so today we'll be hearing from Clayton Cantrall. He's a relatively new postdoc here at Johns Hopkins Applied Physics Laboratory. He has a background in optical remote sensing technologies and in statistical learning methods. And he'll be telling us today about progress in the upper atmosphere, far ultraviolet satellite radiance data assimilation. So Clayton, thanks for joining us today and talking to us, and feel free to start.
Okay, great. Thank you. Are you seeing the?
Yes, looks good.
Okay, cool. All right, so hi everyone. Thank you all for being here. Today I'm going to talk about progress being made in upper atmosphere far ultraviolet satellite radiance data assimilation. And I know that's sort of a mouthful, but what it is basically saying is that we are simulating far ultraviolet radiances that are emitted from the upper atmosphere, mostly the thermosphere. And they're measured by instruments on satellites. And by assimilating these radiances, we are looking to improve thermosphere specification. This work was all part of my PhD under the guidance of Tomoko Matsuo at CU Boulder, with lots of support from Adam Kubrick at NOAA SWPC. I'll be particularly focused on the temperature signal in the FUV radiances and the assimilation of the signal in NOAA's whole atmosphere model, or WAM. And WAM is the model that's used within the now operational whole atmosphere model data assimilation system, or WDAS. And I think this will be a relatively short talk, but there's still a lot of work to be done on this topic. But hopefully this will gives you a good understanding of why we are pursuing FUV radiance data assimilation, how are we developing this capability, as well as highlight the potential impacts. So with that, I'll jump in. Oops. Okay, so the figure shows the vertical structure of Earth's atmosphere, starting with the lower atmosphere, which is comprised of the troposphere and stratosphere, then the mesosphere, and finally the thermosphere. And the drivers of the thermosphere from the lower atmosphere are primarily upward propagating waves that are highlighted in purple, and the drivers from space are highlighted in red, where these sources are the absorption of solar radiation and heating concentrated at high latitudes as a result of geomagnetic storms. And currently, our understanding and ability to predict the global thermospheric response to these drivers, particularly on timescales of weather, is limited. And this is in part due to limited observations of thermospheric states, and also, I guess, as a consequence, due to a current I guess we would argue underutilization of observations of thermospheric states to improve model predictions through the process of data assimilation. So one of these thermospheric states with few observations and with limited progress in assimilation techniques, or the development of assimilation techniques, is temperature. And temperature is a key prognostic state that is important for understanding the energetics, dynamics, and chemistry of the thermosphere. And historically, the most common source of temperature information has come from ground-based and space-based limb observations, which provide high vertical resolution, but will lack the spatial temporal coverage that is needed to observe global variability, especially beyond climatologies. And another source of temperature information comes from space-based disk observations of thermal emissions. And now these disk observations provide much greater spatial temporal coverage compared to the ground-based, and have been very impactful in understanding and predicting weather in the lower atmosphere. But this source can only be used to probe to temperature up to the base of the thermosphere, around 110 kilometers or so. And space-based observations of far ultraviolet or FUV day glow are a unique source of thermospheric temperature information because, one, they can determine temperature on Earth's disk that is similar to the thermal emissions, providing that much greater spatial temporal coverage similar to the microwave and IR radiances for the lower atmosphere. And because, two, they're sensitive to temperatures at altitudes between 120 to about 100 to 250 kilometers, in a region that's otherwise difficult to access by other techniques. And it's these FUV day glow emissions that are the focus of this work. So before I go deeper into our work, I want to elaborate a bit more on the point made about the impact of infrared and microwave radiances on lower atmosphere weather prediction. And this plot is showing the forecast sensitivity of observation impact, or FSOI, over a 4-year period in the European Center for Medium Range Weather Forecast operational system. And what this FSOI is basically shows which observational data set has the most impact on forecast scale. And you can see here in this plot that the top 3 observational data sets are microwave and infrared observations that are measured from satellites and are sensitive to both water vapor and temperature. And also on this plot, there's conventional data that is like dropsondes, radiosondes, and I think many other data sources. There's also aircraft data, IR water vapor, GPS radio occultation, as well as scatterometer data. And a major reason that the IR and microwave observations have the largest impact is due to the fact that they have the much greater spatial temporal coverage that I've already mentioned, including over oceans, compared to the other techniques. And they're also able to probe many different altitudes. That adds a much greater capability. And for a long time, it was the temperature measurements from these 2 sources that were the most impactful. But with increasing accuracy of all-sky radiative transfer, meaning you can radiative transfer in moist conditions, so where there's water vapor within the atmospheric column, and that radiative transfer has improved over time. So you don't just have to use like the clear sky conditions, and as a result, the water vapor measurements have become more and more impactful. Now, most of the time in these operational systems, the raw radiances are actually what is assimilated, as opposed to a retrieved product from the radiances. And there are 2 primary reasons for this. The first is to mitigate errors introduced due to inconsistent assumptions in the retrieval process and forward models. A lot of times those are the radiative transfer models. And the second is to make quantification of the error characteristics more straightforward. This is not to say that retrieve products are not valuable in numerical weather prediction. There are cases where actually the retrieve products lead to a greater forecast skill over the radiances. But in general, the trend is that assimilating raw radiances is the general trend in the lower atmosphere community, at least for the IR and microwave data. And that is really, I guess, a major motivation for the techniques that we take here. So there's also been important results in the past decade that show the positive impact of IR and microwave radiances in the specification of the mesosphere lower thermosphere, or MLT. In studies with NCAR's WACM-X, NOAA's WAM, and Navy's NavGem have all shown that assimilating retrieved products and/or raw radiances from the surface through the MLT has the potential to improve MLT specification. And this is primarily a result of constraining the spectrum of upward propagating waves reaching these MLT altitudes. And the figure on the left just highlights this point with results from the NavGem system, the Navy's NavGem system, showing how the amplitudes of the tidal and planetary waves reaching MLT altitudes are better constrained when assimilating different combinations of observations. In this case, it's SABRE MLS and SSMIS. So the figure on the right shows the observations that are actually assimilated into what altitudes in this NavGem system. You can see that the retrieved temperatures from SABRE, as well as the microwave radiances from SSMIS, are assimilated to about 110 kilometers, which is about the max altitude where you can trust the information content in these observations. And the model top for the NavGem system at this time is about 120 kilometers. But WAM and WACM-X extend to the exobase and provide an opportunity to assimilate observations much higher into the thermosphere to potentially improve specification even throughout the whole thermosphere. And then the next prominent radiance source as you move higher into the thermosphere is airglow. And that is both visible and FUV. But again, we're focused on the FUV. So remote sensing of Earth's FUV emissions has proven to be a powerful technique to probe Earth's thermosphere. And this figure shows an early broadband FUV image taken from the moon, where you can see the major features in Earth's FUV emissions, including the aurora near the poles, as well as the night glow and day glow, where the day glow is on that kind of the left hemisphere there. Now, if we could spectrally resolve the day glow in this image, we would see the N2 Lyman-Birch hot fields, or LBH bands. The figure on the top right shows the LBH band system over about a 30 nanometer bandwidth. It's about the same that gold measures at different temperatures with some of the major bands labeled. Zooming into just that 2-0 band on the bottom right figure, which denotes the transition from the second vibrational level in the excited state to the 0th vibrational level in the ground state, we can see that temperature signal more clearly as this effective skewing of emissions to longer wavelengths with increasing temperature as higher rotation levels in the molecule are occupied. And this is the temperature signal that we ultimately want to utilize. So one of the recent missions to probe these LBH bands is NASA's GOLD mission. And GOLD provides a global scale perspective of the LBH bands on the disk and LEM, but we're focused on the disk from geostationary orbit. That is very similar to the view provided by the microwave and IR sounders for the lower atmosphere. And the figure is just an example of the GOLD measured, in this case, broadband LBH radiance over the course of a day. And these radiances are ultimately an opportunity to greatly increase the thermospheric temperatures data set that can be used to investigate, hopefully global scale weather-like variability. But there are challenges in extracting geophysical parameters like temperature and gaining physical insights from the disk data. The first two challenges that are noted at that bottom box are really inherent to the Lbh day glow emissions. One of them is the asymmetric local time sampling, which does not provide that complete spatial nor that complete global coverage needed to quantify the global patterns of variability. And also the difficulty in interpreting and validating the retrieved disk temperatures due to the Lbh band's broad vertical emanation region in the thermosphere. And I'll get into that a little bit more in a few slides. And then the third challenge points to a broader observational and modeling limitation, and it really motivates the synthesis of observations and models for a more comprehensive representation of the thermospheric state. So given these opportunities and challenges presented by GOLD, a major goal of my PhD work at CU was to help open a new paradigm of satellite FUV radiance data assimilation in the thermosphere to help overcome some of these observational and modeling challenges, while also allowing for the synthesis of the Earth and heliophysics observing systems for forecasting of thermospheric weather. So for the rest of this talk, I'll summarize the work towards this goal with our results this far. I'll also start with providing an overview of the approach, then discuss the radiance data that we assimilate, the information content. Then finally, I'll go into the assimilation experiments, first using synthetic gold data in a prototype data assimilation system, and then go into experiments with real gold data in NOAA's whole atmosphere data assimilation system. Okay, so the overall approach is summarized on this slide. And starting on the left, the thermosphere state is provided by NOAA's WAM. This models an extension of the global forecast system that is one of the sources of our daily weather forecasts. And it's extended up to Earth's exobase around 500 to 600 kilometers, depending on the solar conditions. The forward model that maps the thermospheric states to observations is actually comprised of 4 different models, including NCAR's global air glow model, which produces air glow volume emission rates, a vibrational rotational band model that captures the temperature signal in Lbh bands, a radio transit model that then produces the top of the atmosphere radiances that GOLD actually measures from the volume emission rates, and finally the GOLD instrument simulator. And the output of the forward model is then synthetic GOLD daytime disk observations represented by that data cube on the far right. That has 2 spatial dimensions, 1 spectral dimension with 800 spectral bins between 130 and 160 nanometers. And again, I'll just emphasize that we are simulating the radiance data provided by GOLD, so the level 1 data, and not the retrieve level 2 product from GOLD. The GOLD also provides it's called the T-disk product. It's a level 2 retrieve temperature. So before I go into the assimilation experiments, I first want to go a little deeper into the Lbh temperature signal and define the specific observation from the radiance data that we assimilate that captures that temperature signal. The figure on the left shows the mean Lbh spectrum in gray over the GOLD bandwidth. And the black lines are 2 modes of variability about the mean spectrum. The dashed black line is just the scaling of the mean emission across the bandwidth, while that solid black line is, you can barely see here, is the temperature signal. So moving to the figure on the right, we've zoomed into this little red box where you see the temperature signal denoted by that solid black line more clearly over just the 2-0 bandwidth. The shape of the 2-0 band for 5 different temperatures is also shown in this plot by the colored lines. The vertical line going down roughly the middle denotes the boundary between wavelengths with emissions that are positively correlated with temperature on the right and negatively correlated with temperature on the left. And from this realization that there's this sharp boundary in these correlations, we can define a simple ratio that is the sum of all wavelengths with emissions that positively correlate with temperature, denoted as channel B, divided by the sum of all wavelengths negatively correlated with temperature, denoted as channel A. And this ratio is called the two-channel ratio. It is linearly related to temperature by the operator bold base HR, and it is the observation that we assimilate. And so by defining this ratio, we can capture the temperature signal with a single observation that represents the relative intensity between two channels. And I won't go into more detail here, but there are some other nice properties with this simple ratio as the observation that are associated with the uncertainty quantification, as well as some instrument requirements. So we've established this relationship between our observation and the temperature, but because GOLD is a remote sensing mission, we also need to understand where the observations are coming from in the atmospheric column as a function of viewing geometry. This figure shows the Lbh contribution function for four different combinations of solar and observing zenith angles. The contribution functions quantify how much each altitude contributes to the top of the atmosphere observation. And you can see that the different different altitudinal regions are probed with varying viewing geometries, meaning that the peak of the function changes. And you can also see that the full width half max of these contribution functions is large, spanning up to 75 kilometers in a thermosphere region where there's very sharp temperature gradients. And that means that there's many temperatures contributing to the ratio that we see at the top of the atmosphere, which can make interpretation of the retrieved temperatures challenging without a forward model. So even though there is this nice linear mapping that we showed from the single temperature to the two-channel ratio, when it comes to determining the contribution from each altitude to the top of the atmosphere observation, there is much greater complexity. And this is hopefully all captured in the Lbh forward model that I described previously.
Clayton, this is Valery. Could you basically make a definition of what you mean contribution function? Remind me. What is that?
The contribution function is quantifying how much each altitude contributes to the top of the atmosphere.
No. In terms of the sensitivity of measured emission signal to observable parameter.
Can you repeat that?
It looks to me, according to my memory, contribution function of Stan Solomon introduced with sensitivity to molecular oxygen, actually. Is it correct or not?
Molecular oxygen?
Yes.
Molecular oxygen is the primary absorber, so the extinction.
Yes, exactly.
But it's also a result of the volume emission rates in the
yes,
photo.
volume emission combination of two, but basically mainly to molecular oxygen. It's according to my memory and according to I'm not sure. Basically, this is a big question. Can we use this contribution function as a proxy to make vertical sensitivity of a temperature or constituents to mapping in the vertical space? It's just Conan. I'm not sure. Maybe I was thinking maybe you basically investigate this problem. For me, it was a big quiz how we can use these parameters to do vertical mapping.
Yeah, you're referring to localization?
Yeah, no, that's not localization. This is another story. This is too difficult. But I'm talking about how to basically to do inverse mapping from the point-wise measurements to a vertical grid. But if you don't know, let's continue because this is difficult topic. It's not easy.
Maybe Clayton, why don't you just explain how you computed this?
How I computed the contribution function.
Uh-huh.
This is all from doing sort of like ensemble simulations of the Lbh forward model with WAM.
It's basically output of glow model.
Yep. Yeah. Essentially, yeah. Output of the glow model with the radio transfer component.
Yeah.
Yep.
So this is not sensitivity to the measurable parameter.
No. This is, yeah.
This is just characterization of a measured emission.
Correct.
Okay, thank you.
Okay. Yeah, sorry for that misunderstanding.
No, that's fine.
Okay. So now jumping into the data assimilation experiments. Our first goal was to assess the feasibility of assimilating the gold disk radiances into the whole atmosphere model to improve specification of three-dimensional thermospheric temperature structure. To do this, we took an ensemble data assimilation approach. In ensemble data assimilation, an ensemble of model forecasts describing the prior distribution of the state is updated to the analysis ensemble describing the posterior distribution given observations, such that this update is consistent with the Kalman filter equation. And some key benefits of the ensemble data assimilation are the use of a nonlinear forward model. That is in our case, it's that Lbh forward model. And we don't have to necessarily linearize this model, as well as we can use a nonlinear forecast model. And with that, our background error covariance is dynamically evolving. So data assimilation is typically implemented as a cyclical process between a forecast and measurement update step, but the focus of this work is right now only focused on a single measurement update step, and that's important to keep in mind. So to test the feasibility of assimilating the gold radiances as a prototype ensemble data assimilation system was constructed as follows, and I'll start at the top left and kind of work clockwise. Our updated states are temperature profiles from right here for 100 to 500 kilometers over the disk, viewed by gold. We use an ensemble of model forecasts and predicted observations to compute the covariance that determines the relationship between the temperature at each pressure level and then the top of the atmosphere radiance. WAM is the forecast model. The forecast ensemble is generated with a stochastic perturbation model based on SDLO Eve and time C spectral bands defined in the Solomon 2005. And an ensemble scroll filter is used for the assimilation. The assimilated observations in this study are two-channel ratios computed from synthetic gold observations generated from, in this case, a TIGCM truth run. So the figure shows examples of the measurement update at two locations on the disk. The first ensemble, the forecast ensemble is shown in the light gray. And the best forecasted estimate is the mean of the ensemble shown by the dotted line. The true temperature profile is shown by the solid black line, from which we generate the synthetic observation. When this observation is assimilated, the ensemble is then updated to the measurement updated ensemble shown by the dark gray lines, where the new best estimate is the dashed line. And there are two positive outcomes that you can see here from the assimilation of the synthetic observation. The first is that there's a reduction in model bias as the model, as the measurement updated profile is closer to the truth than the prior. And second, there's also a reduction in model uncertainty that can be seen in the smaller spread of the ensemble. And note here that in the second plot, the measurement updated temperature profile does not completely capture the temperature profile in the lower thermosphere. And this is partially a shortcoming of this technique due to the fact that this is an underdetermined problem where we're trying to estimate many states from basically a single observation at the top of the atmosphere. So this figure now shows the measurement update over the date side disk during a geomagnetic storm at 4 different thermosphere pressure levels. The first column is the TIGCM truth temperatures. The second column is the WAM forecast temperatures. The third column is the forecast temperature bias. And then that last column is the measurement updated temperature bias. And from the forecast to the measurement update, the model temperature bias is reduced by 40%. The model uncertainty reduced by 18% in the lower middle thermosphere. And then in the upper thermosphere, the model temperature bias is reduced by 60% and model uncertainty by 25%. So these are, I guess, very encouraging preliminary results that suggest this new framework to assimilate gold FUV radiances can improve the three-dimensional specification of temperature in NOAA's WAM. The better performance in the upper thermosphere compared to the lower atmosphere, compared to the lower thermosphere, can be at least partly attributed to how the ensemble was generated. We only perturbed solar radiative forcing, which created greater model uncertainty at the higher altitudes, then allowed for the model to be more readily corrected at those altitudes when new observational information was present. But in the experiments to come, we also perturbed the lower atmosphere conditions with the intent to create greater model uncertainty in the lower thermosphere. Okay, so now moving on to the next set of experiments that builds off these previous results. The goal now here is to develop a new capability to assimilate gold disk radiance data into NOAA's whole atmosphere model data assimilation system, or WDAS, and then assess the impact on the specification. In this case, not only on temperature but also composition. And the figure is providing just an example of WDAS predicted densities at 400 kilometers altitude over a few day period in May 2021. And WDAS has been operational since July 2021 and is currently assimilating tropospheric and stratospheric observations. But as far as I know, as of yet, has not yet assimilated thermosphere or ionosphere observations, at least in an operational sense. And this means that there's exciting opportunities to incorporate new observational data sets into WDAS, and not just FUV data. So in this case, for this experiment, we are using the same Ensemble data assimilation approach with an Ensemble square root filter as taken in the previous experiment. The differences now are that we are using the operational software modules, real gold disk data as opposed to the synthetic, and we're updating both temperature, thermosphere temperature and composition. So WDAS uses WAM as the forecast and the grid point statistical interpolation, or GSI, for the assimilation of the measurement update. And again, we're only focused on a single measurement update, which is handled by GSI. So that I'm going to focus on that here. So to assimilate the gold data into the operational system, we needed to integrate the gold data processing routines, uncertainties, and the Lbh forward model into GSI. And the figure just depicts the GSI structure. The figure on that kind of the far right depicts the GSI structure and the overall additions, which are shown by kind of the additions, meaning the routines in the green box, and as well as modifications in the yellow that were made to this code base. One of the benefits of GSI is that there's many ways to solve the data assimilation analysis, both variational and common filter based approaches, as well as hybrid approaches between them. But again, we're just going to stick to the ENKF implementation. And just note that while we are only assimilating gold observations for this proof of concept, there is now the potential capability to assimilate gold observations for the rest of the operationally assimilated observations from the troposphere and stratosphere. So for this experiment, we generate an 80-member WAM ensemble by perturbing both solar geomagnetic and lower atmosphere initial conditions. This figure is just giving you a visualization of the ensemble at the time of the assimilation experiment, in this case on November 4th, 2018 at 12 UT. The first row of the figure shows the mean of the ensemble for temperature in the first column, O to N2 in the second column, and density in the third column. And the second and third rows show the standard deviation and percent standard deviation respectively. And I guess it just note in the O to N2 and sort of that middle figure, the kind of the high uncertainty within that higher latitude region, that band, because I'll refer back to that in a moment. But we use 6 solar geomagnetic inputs to, we perturb 6 solar geomagnetic inputs based on their temporal variance. And these include F10.7, KP, hemispheric power, solar wind, speed and density, and then VZ. And then the perturbed lower atmosphere initial conditions are provided by the National Center for Environmental Prediction Global Data Assimilation System Ensemble, and then extended to the thermosphere with MSIS. So this figure shows that the temperature increments delta T at 4 different pressure levels in WHAM after simulating the gold data. The increments are computed as the mean of the measurement update ensemble minus the mean of the forecast ensemble. So blue means that the model temperature decreased by the assimilation of gold. Red means temperature increased. So at this time, WHAM temperatures generally decreased in the higher latitudes and increased in the lower latitudes by the assimilation of gold. You can see that the updates are localized around the observation locations on the day side, which is controlled by a horizontal localization parameter. There's still quite a bit of work that needs to be done to kind of tune this localization parameter. Right now, it's kind of a static value, but I think in the future, it's going to have to be kind of a varying value. But anyway, so the figure on the right then shows how the increment profile, what the increment profile looks like at one latitude, longitude point. And the verticalization localization is apparent in this figure by the peak increment occurring around the peak of the Lbh contribution function and tapering off in either direction. And in all these, we're using a Gauss cone localization function. So even though the assimilated 2-channel ratio is directly sensitive to temperature, other states such as composition can be updated through the background air covariance. Here, the column O to N2 ratio increments are shown. And column O to N2 represents, the compositional changes of the 2 dominant species in kind of the lower thermosphere. The most significant change in model specification of the O to N2 after its assimilation is observed between that 30 to 60 degrees north region, again, that I highlighted before, where you saw that great in the most uncertainty in the forecast. Now, unlike temperature, where there are very few independent sources to compare against, in the case of O to N2, we can directly compare against gold retrieved O to N2. And in the left plot on the figure on the right shows the gold O to N2 product at the same time of the 2-channel ratio assimilation. The rightmost plot shows the change in the root mean square difference from the forecast to the measurement update with respect to the gold retrieved O to N2. And so here blue means that the measurement updated WHAM O to N2 ratio is closer to the gold O to N2 than the forecast. At this time, there's a modest decrease in the RMSD of 3% over the disk, but there are regions, particularly in that higher latitudes, that see a 10% decrease in RMSD, meaning WHAM specification of O to N2 is in better agreement with the gold retrieved O to N2 after the simulation of the 2-channel ratio. And just remember that these results are only a single measurement update, and we expect better performance, or I'll just say that the performance will change when gold observations are assimilated over a longer period of time. But nonetheless, this is an example that by assimilating gold radiances, we can update the thermospheric structure beyond temperature, such that the model is in better agreement with independent observations. And the reason I say independent is the information that we're taking from the Lbh bands is different than that is used for determining the O to N2 ratio. And the O to N2 ratio, you're using the kind of the absolute intensities and not the shape of the emission features. So to summarize, in these 3 experiments, we're on our way to building out and testing a satellite FUV radiance data assimilation capability with WHAM. The framework has been constructed And these experiments have shown that there is significant impact in assimilating FUV radiances on WAM specification of the thermosphere. And we found that this is true for both geomagnetically quiet and disturbed periods, although in this case I really just focus on the disturbed. And it's not just the temperature structure, but also composition, and as a result, potentially mass density as well. So in looking from a broader lens, these new capabilities support the routine ingestion of FUV data and ultimately the future synthesis of heliophysics and Earth observing systems for monitoring of thermospheric weather. There's still a lot of work to be done that's being carried out in Tomoko's group at CU with the support of Adam Kubrick. The global workflow, including WDAS, has been ported to NCAR's Cheyenne HPC. So we can now cycle between measurement update and forecast instead of just that measurement update, which I have shown. But before these cycling experiments are performed, the Ensemble capability within the global workflow needs to be introduced, which is another significant chunk of effort. And that will allow the Ensemble score reveal to be used instead of what is now used, which is the 3D VAR approach. So the 3D VAR approach is what is used in the kind of the operational context. So once that is accomplished, we can actually do like the true observing system simulation and also observing system experiments that will be carried out with both, that could be carried out with both GOLD, the FUV data, as well as there's also a strong push in Tomoko's group to do the cosmic radial occultation data to update WAM IPE, not just WAM. So as a final point, I just want to highlight that this work is focused on the temperature signal, which is just one of many possible observables that can be utilized in the FUV spectrum. This table is highlighting the major FUV emission features defined by the columns. You can see the red box just kind of highlighting the one kind of signal we've been after. And these emissions features correspond to different atomic lines or molecular bands that are either produced by photoelectron impact excitation and or solar resonance scattering. And in going across the top, you can see the hydrogen atomic line, two atomic oxygen lines, a nitrogen line, the N2 Lbh bands, and then the NO bands. And the insight that each of these emission features provides is sort of a unique look into the thermosphere ionosphere state, and can vary depending on the different viewing conditions, whether that be day, night, aurora, or limb and disk, and that's all kind of summarized in this table. And you can see that the FUV emission features are sensitive to a huge range of phenomenon in the thermosphere and ionosphere, including the concentrations of the major constituents, and also important energy exchange processes like electron precipitation. And it's, I guess conceivable that at least some of these observables beyond temperature can be assimilated to improve ionosphere thermosphere specification in the future. And I'll just highlight a couple here. So one is probably the most obvious is to consider assimilating is the O to N2 ratio observed over the daytime disk. The figure that I show here is the GeoDAWG O to N2 ratio observations during a geomagnetic storm over the course of a day. And GeoDAWG, GOLD, and ICON are all providing O to N2 data. And so there's an unprecedented spatial temporal coverage that could be used to support an in-depth investigation into the impact of the O to N2 on global thermosphere ionosphere specification. I'll note though that there is quite a bit of work that still needs to be done to cross-calibrate the O to N2 ratio between these three missions. And it may actually turn out that O to N2 is it may be less valuable, and we actually just want to assimilate the radiance intensities from each of these lines. But that is all work that can be done in the future. Another and more far out observable to consider is that sensitive to NO. This figure is showing the NO column density derived from GeoDAWG during the peak of a storm on the left, and 2 days after on the right. And although it's a minor constituent, NO plays a major role in the thermosphere energy budget, and NO observations can possibly be used to help models better predict the storm time response, and particularly the storm time recovery. This is definitely more far out, especially for WAM, because I think at this time WAM does not include NO explicitly. So these are just 2 examples, but hopefully it gives you the impression that there's a lot of exciting directions to pursue in terms of satellite FUV data assimilation in the thermosphere ionosphere. Much of the groundwork is in place, or is close to being in place, to really understand the impacts of these unique and important observations on ionosphere thermospheric predictability. So just to summarize, there's exciting opportunities and challenges with current and future FUV observations and the Heliophysics Observatory for data assimilation. We focused on gold here due to the perspective that is provided at geostationary orbit, but these techniques are not limited to gold. FUV observations can be used to update key thermospheric states in first principle models like WAM, including temperature and composition that we focused on here. But I think once we're able to cycle, we can also investigate updating winds as well as other minor constituents. There's still work to be done to build out this data assimilation capability, but these preliminary experiments are complete and show significant potential. So with that, I'll stop and turn it over for questions. And thank you everyone for listening.
Thank you.
Nick, go ahead.
Yeah, thanks, Clayton, for a nice presentation. Just quick question: how did you deal with the error specification for the direct assimilation of the radiance data?
For the observation?
Yes.
Yeah, so that was a pretty large chunk of my PhD work. I did not go into it here, but it was a lot of it was related to the ratio. One of the nice properties of the ratio is linearly related to temperature. So it makes it a little bit easier to perform the uncertainty quantification. But for me, it was a lot of Monte Carlo simulations, as well as there's the different there's the measurement error as well as the representativeness error that all need to be specified. The representativeness error is made easier to specify because of the ratio specification, as opposed to just using the absolute radiances, where you need to understand all the biases that could potentially be included in the model to produce the absolute radiance. But because of the ratio, we only really need to focus on the relative intensities, and there's not many error sources in the model that contribute to just that relative intensity bias. I don't know if that answers your question.
Yeah, somewhat. So it's not just related to, I guess, instrument sensitivity. It sounds like there's quite a lot that goes into it.
Well, it's two. Yeah, so it's the instrument sensitivity and then the representativeness error, and it's I guess the representativeness error is just made simpler. The quantification of that is made simpler by using that ratio instead of the absolute intensities.
Right. Okay. Thank you.
Larry, go ahead.
Yeah, basically, first of all, I would like to thank you and Tamoka for starting to do with wonderful stuff, because we definitely need this Radiance Data Assimilation capability for, especially for thermospheric composition and temperature. And basically, you show that you will be able basically to do infrastructure for operational model and basically to show some encouraging results, first results, of course, in terms of FOSI. So it's a big way forward to introduce this to operation. But I think it's basically first step is done, and we can consider how we contribute further using new data assimilation capability like GeoDAWG, etc. So I basically just recommend, if you will be pursue with study with gold data, so to concentrate probably on the not O(N)2 ratio, but assimilation of partial columns of atomic oxygen and molecular nitrogen. So you will demonstrate basically by doing assimilation to emissions observed by gold capability to retire with very wonderful characteristics like O(N)2 ratio towards the partial column. The reason why I would like to suggest you, because O(N)2 ratio, it's a good characteristics and simple characteristics, but what gold has actually measured, it's partial column of atomic oxygen, molecular oxygen, basically shaped by these emissions, OI and Lbh. So this will be interesting to assimilate two emissions and compare assimilation of two partial columns versus somehow to compute also O(N)2 ratio, compare with operational product. Probably this will be very, very much interesting line of research. Basically, we can discuss with offline, of course. I don't like basically to spend a lot of time of people who attended with your seminar. But a couple, two technical questions. First of all, why you selected 80 members of Ensemble? This is basically legacy of Jeff Whitaker's suggestion to use 80 members in NOAA Ensemble data simulation system.
Yes, yeah, exactly.
And second question, technical question is, what's the time window for assimilation?
So again, this was only focused on one measurement update. We weren't doing cycling.
Okay, so
but in the future, I expect that, just you're probably going to have a relatively high frequency of assimilation of, specifically with the temperature.
And the proxy to, and the last one is a proxy to mapping to the model space used with contribution functions depending on solid angle.
Sorry, can you repeat that, Vali?
Yeah, basically, when you do misfit between radiances, you need to map back from radiances misfit or your signal, what you introduce, back to a temperature space. What's your tangent, transpose tangent to map from the data space to the model space?
So it's the when we
inverse operator. How you do inverse operator?
I'm sorry. So
did you modify? More simple question. Did you modify something in the Ensemble square root filter of GSI?
We didn't modify how the localization is formed, but we just specify based on the peak of the contribution function, like that. That's where we localized, and then we use the Gauss-Cohn function to localize around.
And it depends, and it's pixel dependent, or it's just basically universal, or with dependence from solid angle.
It's pixel dependent because we have that full Lbh forward model within GSI. We can grab that and we can compute that whole contribution function for that given time and in conditions, and then pick out the peak of the contribution function at that time.
All right. Okay, so we would expect that you are adjusting temperature in the higher latitudes at higher heights, right? Under the higher solar zenith angle.
It is, yes, there is a solar zenith angle.
So the major impact at latitudes something like above 50 degrees north and south will be above 180 kilometers, right? Correct?
180?
Yes, something like this, not 150.
Um,
Because contribution function basically maximize significantly higher.
correct. Yeah, the higher solar zenith angle, that
Yeah.
kind of the higher the peak.
Yeah.
And that, yeah, that can range from anywhere from 140
Okay.
at 0 and to, yeah, about 180.
Okay. Thank you.
Yeah, yeah, thanks for your comments, Valerie.
And Nick?
Yeah, hey Clayton, nice talk. I was wondering if like you would see different filter performance or update performance at like a 0 zenith angle versus on the limb where you have a higher zenith angle, or there's too many other things complicating it to really kind of attribute it to that, or if it's just like an important consideration.
It's definitely an important consideration. I can't speak quantitatively to that right now. But one thing that is going to be important going forward, especially with gold, and is how that the localization, the horizontal localization is performed, which is going to impact the filter performance, whether you're kind of close to the center of the disk or on the limb. Also, as you go to the higher solar zenith angles, your sensitivity and the altitude in the atmospheric column is kind of greatly expanded. So you have less sensitivity to one particular altitude, and I expect that's going to affect the filter performance. But again, none of this has really been quantified in detail, and will need to be once we can actually, we're doing the cycling and the kind of do more robust simulation experiments.
Cool. I guess, do you calculate or uncertainties for the higher zenith angle? I forget your plot for showing those.
Do I have uncertainties?
Yeah, I guess you have a higher uncertainties for like the higher solar zenith angle.
You mean as far as like where the shape of the contribution function?
I guess so, yeah.
I wouldn't necessarily say you have higher uncertainties. Yeah, it's still, I think it's, maybe when you get really close to the limb, probably, but in like the 60, 70, 80 degree solar zenith angle and observing zenith angle, and it shouldn't be like you have greater uncertainties with increasing angle. It's all, I guess, specified in the forward model.
Okay, makes sense.
And Chuan Ping?
Hi, Clayton. Nice talk. A quick question I'm wondering is the step vector. Is any just the neutral temperature in your step vector? Is any other like neutral state like geopotential height or other wind fields in your step vector?
Yeah, you're asking if we're updating any other states?
Yes.
Yeah, so right now all we looked into is temperature and composition. But yeah, I expect with time, like there's more states will be looked into as far as the impact of the gold observations on their specification. But yeah, right now it's just temperature and composition.
Great. Good. Thank you.
Yeah.
Are there
Right.
any other questions?
Clayton, that
All
was a
right.
great job. And then I like to follow up. There's one master student who is working on, I don't know if you met Brandon, who cannot make it today. So I'll follow up with you too.
Okay, great. He's working
well,
on. No, yeah, we can talk later.
Yeah, go for it, Clayton.
No, it's okay. We can.
He's taking an apprenticeship with Akash and Adam to do
Okay,
cycling.
Okay, okay, that's
You can use
great.
your ensemble as example, and then pass it back to you. You
Okay.
can find time to complete.
Okay,
Mhm.
great.
Well, I think we're at the top of the hour, so we'll wrap up from here. But thank you so much, Clayton, for a really wonderful talk and generating a lot of great discussion. We're excited to see where that goes in the future. Thank you all so much for coming to this seminar. We look forward to seeing you in a month for Umberto's talk on November 1st. So please make sure to come back here on the other side of Halloween to catch that talk as well. And we will let you all go. Hope you guys all have a good month, and we will see you soon.
Thank you.
Thank you.
Thank you.